here in the second part of its tutorial. Go ahead.
All right, thank you. So on my first talk, I took the word higher off, and we talked about the binary commutator, and now I put the word higher back so we can talk about commutators of more than two variables. Okay. I'm starting with a recap on the two variable commutator. So think that we have an algebra in mind, and it has congruences alpha and beta. They're kernels of homomorphisms. And the commutator is a way of computing another kernel from alpha and beta. And I focused on what I call the rich structure situation, congruence modular varieties, where the commutator has better properties that are better understood. The definition makes sense for any algebra, and in fact, it makes sense at a categorical level. But in the congruence modular case, some of the things that we mentioned were that if you have some congruences on an algebra, the commutator is a monotone operation. So if you increase alpha and beta to alpha prime, beta prime, then you will increase the value of their commutator. The commutator of alpha and beta is contained in alpha and in beta, and therefore the intersection. So we say it's a sub-multiplicative binary operation on the congruence lattice. It's symmetric. Okay, this is in the congruence modular setting. It's symmetric. It's not always symmetric in pathological settings, but I will say it's additive. Additive with respect to lattice join in the congruence lattice. That is, if you join two in the first position and you want to take the commutator of alpha, join alpha prime with beta, you can take the commutator of alpha with beta, the commutator of alpha prime with beta, join the results. Because it's commutative in the congruence modular setting, I have this in both variables. Also, did I say it's continuous? Yes, I did. I said it's continuous. That means it respects up-directed unions. Congruence lattices are algebraic. Okay, so we're interested in operations that preserve up-directed unions. And that gives us that it's actually completely additive in each variable. I can distribute it over an infinite join. Okay, so that an infinite join of alpha is commutator beta is just the infinite join of each alpha commutator beta. It has good properties with respect to the constructions, formation of homomorphic images, formation of subalgebras, formation of products. What are those good properties? Whatever you think should be true for groups or rings. Okay, so if I were to take a product of two groups and take two product normal subgroups and take their commutator, I can compute it coordinate-wise. If I have a group and I have congruences on a group and I restrict them to a subgroup, then the commutator on the subgroup is going to be smaller than it would have been just if I took the commutator in the whole group and restricted the result. Okay, so it's what you would expect from groups and rings. And the thing that I think is interesting is that the commutator encodes information about model creation. So if I have an algebra in a congruence modular variety and I know its commutator properties, then the definition of the commutator allows me to build a quotient of a subdirect square of the algebra. And it's possible to start with a moderately small subdirectly reducible algebra and build a larger subdirectly reducible algebra using information from the commutator. Okay, so that's the usual constructions of HS and P don't obviously tell you how to produce larger subdirectly reducibles. Okay, and as I say here, there are other operations that have these properties. The most obvious one is just the identically zero operation. I could create a new thing called a commutator. Just say the commutator of any two congruences is zero. That's a commutative operation that respects complete joins. That's below the meat. I don't know if it encodes information about model creation, but you could trivially define something that give me an algebra, take two congruences, just by fiat say their commutator is zero, and then create a model by handing you back the algebra, do something like that, something silly. So we would like to know that there's something about the commutator that makes it non-trivial. Okay, something about the commutator that makes it not just the constant zero operation. And I want to say that if you want this theory to be non-trivial, you want the statement that one commutator 1 equals 0 to be a non-trivial statement. You don't want any two congruences to commutator to 0. In particular, by monotonicity, that's the same as saying you don't want the largest congruence commutator itself to be 0 always. So that should be very restrictive. And in the case of groups, we're saying an abelian group has very special structure. Okay, or a congruence alpha. If alpha commutator alpha is 0, that should say something very strong about alpha. And if I have an alpha and a beta and they commutator to 0, that should be a strong statement about how alpha and beta are related to each other. Okay, so that's what makes it non-trivial. Is maybe I'll focus mostly today on the one commutator 1 equals 0. I want that to be a strong statement if the commutator theory is going to be non-trivial. Now, that's a recap of what we discussed on the binary commutator. I want to move to multivariable commutator, higher than 2. But before I do, I want to mention that there are lots of other binary commutators. And I mentioned a couple yesterday, but I'm going to mention a couple more that have nice, simple descriptions. This is the commutator given by the two-term condition. So I'm going to recall, we talked about alpha beta matrices last time. They were defined by, take these trivial matrices, 2 by 2 matrices, constant on the rows, okay, or constant on the columns. And for alpha beta matrices, if they're constant on rows, but the element on the first row is alpha related to the element on the second row, then that's going to be an alpha beta matrix. And if the element in the first column, if it's constant on columns and the element in the first column is beta related to the element in the second column, that's going to be an alpha beta matrix. And just close this, just make this a subalgebra of A to the 2 cross 2. That subalgebra will be all alpha beta matrices. If you want to think, or I will express what I'm thinking of when I see this. If I were dealing with an abelian group and I form these things, these types of matrices, what I would be thinking is the alternating sum of the entries is 0. Okay, so do a plus minus checkerboard pattern. And if they're constant on rows, the sum will be 0. If they're constant on columns, the sum will be 0. If you generate a subalgebra in an abelian group with a bunch of things whose sum is 0, the result's going to be 0. So I have very special matrices that come up. I'm not going to get all 2 by 2 matrices this way. I will only get matrices where the alternating sum is 0. And then I can imagine, I can take that information and define a commutator that tells me I'm dealing with an abelian group. It's going to tell me that it's abelian. How? Well, take 2 matrices in this subalgebra, and I want to look at those, and without knowing the addition, without knowing the 0 element of the group, I want to say that the alternating sums are 0. I want to say that. And the way I say it is this. Compare them entry by entry. And if 3 of the entries agree, then the 4th must agree. Because there is this condition, the alternating sum is 0, that's an extra condition on the 4 entries. So if in the first matrix, 3 of them have some kind of alternating sum and it agrees in the second matrix, but each matrix has alternating sum, the total alternating sum is 0, then the 4th entries have to be equal as well. Okay, that's what I'm thinking about this. And this is the basis of a commutator. I can look at, for any algebra with 2 congruences, I can generate M alpha beta, and I can write this implication down. If 2 matrices agree on 3 entries, they must agree on the 4th. And if that's true for alpha and beta, I say alpha commutator beta is 0 in the 2-term condition. This commutator was invented by Emil Kish in the 80s, and his paper appeared in 1992. The 2-term commutator is exactly the same commutator as the one that we talked about last time. For congruence modular varieties. When you move away from congruence modular varieties, it starts to differ from the one that we discussed on Monday. So that's a new commutator. And I want to compare it to another one that Emil worked on with Alan Day, and later Alan Day and Heinz-Peter Goom wrote a follow-up paper on the second one, the free intersection. This is a nice way to think of a commutator of two congruences on a group or a ring. That it's just, you're computing the free intersection. So let's talk about that. We'll start with a variety, have an algebra in the variety, two congruences on the algebra. Now I'm going to introduce a set of variables. I have X, capital X is a set of variables subscripted by A. Capital Y will be a set of variables subscripted by A. And now I want the free algebra on the disjoint union of X and Y. So I want a free algebra that has sets, two sets inside of it that copy A. I have two copies of A are my free generators. One copy of A named by X, the other copy of A named by Y. And now I can look at the congruences alpha and beta, they're equivalence relations on the universe of A. So they are equivalent. I can define equivalence relations on capital X that looks, one that looks like alpha on capital X and one that looks like beta on capital Y. So I define alpha sub X to be an equivalence relation on free generators. X sub A and X sub B will be related provided A and B were alpha related in the algebra A. So I'm copying over the equivalence relation alpha onto some of the free generators. And then I copy over the equivalence relation beta onto some of the free generators. So I have two equivalence relations on free generators, and I generate congruences with those. Okay? Now, the free intersection of alpha and beta is the intersection of the corresponding congruences or equivalence relations, congruences on the free algebra. So I took alpha as a congruence on A. I have a copy of A among the first group of free generators. I have an equivalence relation on those generators, generate a congruence of the free algebra. I do the same thing with beta on the Ys, and I'm going to intersect them in the free algebra. Okay? Now, that's a congruence on the free algebra. There's a natural map from this free algebra to A. You just map little x sub A to A. It's little x sub A represents little a in the free algebra. Little y sub C represents C. I just map the free generators to what they represent. And I push forward this congruence on the free algebra. I see what its image is under this map. And it turns out it's the commutator. This is a categorical way of defining the commutator. You just take your equivalence relations, realize them in a free algebra, form their intersection, push them back onto the algebra. That's the commutator. Okay. We have these two that I just introduced, two new ways of looking at the commutator and congruence modular varieties. And I think if you just stare at them for 5 minutes, you will start to ask yourself this question: why stop at 2? Why stop at 2? Everything we said is completely language independent. There are no special commutator words that have to be referred to. If I talk about the free intersection and I copied 2 copies of A as the free generators and have equivalence relations I have my alpha sub X, my beta sub X, I'm just going to intersect them. Why can't I do that with 3 or 4 or more? And with the 2-term commutator, we looked at 2x2 matrices. And we compared them vertex by vertex, and we said if they're equal in all vertices but one, they must be equal in the last. Well, why 2x2 matrices? Why not 2x2x2 matrices that involve an alpha and a beta and a gamma? Why not do the same thing? Okay, so I think you can't really stare at these very long before you start to think we could create new types of multivariable commutators, and this is how we do it. If I'd known that Connor Meredith was going to bring his nice photo images, I wouldn't have struggled with these images. I would have asked him to give me his cubes. But this is what you would do with the 2-term commutator if you wanted a 3-variable version of the 2-term commutator. You would have these 3 congruences, alpha, beta, gamma. Something's moving here. Move that out of the way. So we have alpha, beta, gamma. In the first picture, if you look at the left face of the cube, they're all labeled A. And the right face of the cube, they're all labeled B. And I want A and B to be related by alpha. So I have left face compared to right face in this cube. In the middle one, I have back face and front face. The back face, they're all labeled C. They're constant on the back face. They're constant on the front face. They're labeled D. And when you move from C to D, I want CD to be in beta relation. And the last dimension, top face versus bottom face. I have E's on the top, F's on the bottom, and I want the pair EF to come from gamma. Now I generate a subalgebra with all of these cubes. I'm going to get a subalgebra of cubes, and I'm going to write down my definition of a two-term commutator. I take two matrices, M and M prime, from this subalgebra, and I say if those two cubes that I picked agree on 7 of their vertices, they must agree on the 8th position as well. Okay, it's a definition of a commutator that involves 3 congruences this time. With the free intersection, what do? We have a set of variables X, we have a set of variables Y, now we need a set of variables Z. And they enumerate copies of A within the free algebra. If you give me an alpha, beta, gamma, then I'm going to define congruences on the free algebra where I look at X and put the equivalence relation alpha on X and generate a congruence. Then I take my beta, I put an equivalence relation on Y that looks like beta, generate a congruence. And then with gamma, I do that on Z. I intersect the results, and then I map it forward back to A once I've intersected it, and I define a ternary commutator. Okay, it's easy to do. But the question is, why shouldn't we do this? And because why would we do it? I mean, what are we going to do it for? What is our intended application? Are they good for anything? Are we reproducing something that's known? So this is a question. You could do this in many different ways. And the question is, why? Where are you going with it? Okay, and answer was 3 question marks. Yeah, I want to say something about that. First, the ternary commutator. Ternary commutator given in terms of the 2-term condition. It's a monotone ternary operation. It lies below the meet. It's totally symmetric. I just wrote that if you swap the first 2, you don't change the value. If you swap the last 2, you don't change the value. And 2 different transpositions generate the symmetric group. So it gives you all the permutations this way. This is really because of the way cubes are defined. There's a lot of symmetry in a cube. You can work out that it doesn't really matter what the result is. Turns out it's additive in each variable. It's a continuous operation. It has all the properties we were looking at. I left off that it's useful for creating new models because I don't know how to use it to create new models, but I think that would be interesting. Is there a natural way to create new models from this commutator? Okay. It has good HSP properties, and that's true not just for ternary, but for 4-ary, for 5-ary, for 6-ary. We can get higher arity commutators with similar properties. Is it good for something? That's the main question. And I'm going to mention a tiny application of this. This involves a little bit of deception. Okay, which is what we're here for. So what's not a deception is that this question was posted by Derek Holt to the group pub forum and later on Math Overflow. He asked a group theoretic question, which is this. Let me put it all up there. I'll go back a little bit. So Derek Holt is a group theorist at the University of Warwick, and he works in computational group theory, and he asked this question. Let G be a subdirect product of finitely many perfect groups. Perfect group means, here, SI is perfect means that SI commutator itself is SI. If you start at the top, at the whole group, and start taking derived subgroups to see how far down you get, you don't go anywhere. The first derived subgroup is itself. It's its own commutator subgroup. That's the definition of perfect. Okay, so start with some perfect groups. And then G is a subdirect product of finitely many. Subdirect product means it's a subgroup of the product, but it projects surjectively onto each factor. Okay. suppose you take a quotient of such a group and it's solvable, must it be abelian? Must a solvable quotient of a group constructed this way be abelian? Okay. And he says it arose in a study of complexity of algorithms for finite permutation groups and matrix groups. All right. Okay. Now, I'm going to say something that involves higher commutators for this question. If the quotient is solvable and there were k factors in the subdirect product, then the quotient will satisfy one commutator, one equals 0, where there are k ones. It will satisfy that condition. So if the quotient is solvable, then the quotient satisfies this commutator condition. And conversely, for any k that you give me, there will exist an example with a g, with an si, with an n, satisfying all the conditions, where the g mod n is solvable and satisfies this condition with k ones and does not satisfy the condition with fewer than k ones. So there are k factors, you're guaranteed a commutator condition with k ones, you are not guaranteed with fewer than k ones. Okay, there's an example. All right, so a higher commutator is coming up in this example, and I'll explain why it's useful. Okay, so I'm just going to talk about the easy direction of this, and that is so G is a group, it has a normal subgroup N. I like to talk about congruences, so I'll use nu in place of N. That is an equivalence relation on the group where the class containing the identity is N and the other classes are the cosets of N. That's all that nu is. It's a different way to talk about N. G is going to be a subdirect product of these SIs, which are perfect. I'm going to let A to I be the kernel of the projection onto the ith factor. Okay. Now, I'm going to introduce new language I don't think anybody else uses, but co-perfect and co-solvable. I will say that a congruence is co-perfect if you factor by it and get a perfect group. And it's co-solvable if you factor by it and you get a solvable group. Okay? So A to I is a projection kernel onto a perfect group. So if you factor by A to I, you get SI, which is perfect. So A to I is co-perfect. Okay. Nu, if you factor by nu, you get G mod n, which is assumed to be solvable. So I say nu is co-solvable. The quotient mod nu will be solvable. Now the interesting thing is that solvability is sort of the opposite of perfectness. If I have a solvable group, any further quotient is solvable. If I have a perfect group, any further quotient is perfect. But you can't be non-trivial if you're both solvable and perfect, because you start at the top of the group and look at G commutator G. If you're solvable, it will come down. But if you're perfect, it stays at the top. Those are incompatible with each other. So if I look at nu, which is co-perfect, co-solvable, and A to I, which is co-perfect, their join, which is above them, must be both co-perfect and co-solvable, but only the top, only trivial groups can be perfect and solvable. So this join must be the top congruence. It's the top congruence of G. It's 1. So this join is 1 for all I. And now I can compute the higher commutator this way. In G, 1 is equal to nu join A to I for all I. Okay? So I look at 1, 1, 1, 1, 1, the higher commutator. I replace each one, the first one with new commutator A to 1, the second one with new join A to 2, etc. Just replace all the ones with what they're equal to. Then I use these properties, the additivity property. I can distribute over join in every variable. And if I distribute a big product over join, just imagine you're multiplying algebraic expressions, just distributing it all out. Every factor will contain a nu in it, except one factor. And that one factor will be A to 1 commutator, A to 2 commutator, commutator up to A to k. But all the other summands, when you multiply it out, will have a nu in it. And because the commutator is submultiplicative, if new appears in a variable, the result will be below new. Okay, so when you spread this out, when you expand it, all the factors will be below new except one, and that one factor will be this one. And this factor, because it's submultiplicative, will be below the meet. But these are projection kernels. These are the K projection kernels. They meet to 0. So this is 0, so we end up with new. So I get that one commutator 1 gets below new. So if you factor by new, one commutator 1 will become 0 in the quotient. Okay, and that's the statement. And it tells us that there's a higher order commutator condition that must be satisfied in this quotient. And you can't do better than that condition with K1s, because we have these examples that show that you can't do fewer. By the way, then Derek Holt, we told him about this, and he did some magma computations, and he found the first example when K is 2 has like 10 to the 15 elements in it somehow, that you really can find a quotient, a solvable quotient, which is not abelian. It's going to have one commutator 1 is 0 with, yeah, right. Okay, maybe my K is off by 1. Okay. In any case, so that's an application of the higher commutator. I'm going to call this quotient where one commutator 1 equals 0 super nilpotent. Connor Meredith introduced the definition earlier, and I'm going to reproduce that definition a little bit later. I'm still talking about, is there a use? Is there a use for this? And this seemed to suggest that there is a use, even for group theorists, where all of this began. It seems that even in group theory, you could learn something more from the higher commutator. That's the deception, though. I say we should not stop at binary commutators. It turns out that for groups, this isn't useful. I'm trying to make it look like it was useful for groups, but I'll confess in a moment why it's not really useful for groups. But I claim we shouldn't stop at the binary commutator. But again, everything we said about the binary commutator, the theory doesn't become useful unless you can rule out that you're adding a totally 0 operation. The statement that one commutator 1 is 0 should be a strong statement for this to be a useful theory. So I'd like that statement to be a strong statement. And also that for a given congruence, if alpha commutator alpha is 0, I would like that to be a strong statement about alpha. And if I have different congruences and their higher commutator is 0, that should be a strong statement about their relationship. Okay, now here's what we know at present. Let me just put these facts up here. Just in the case of the binary commutator, there are competing definitions for what the higher commutator should be. I've already mentioned the 2-term commutator, the free intersection. There's a Bulatov version. That's what Connor Meredith introduced in his talk. There are various versions of the higher commutator. For congruence modular varieties, they seem to agree with each other. Okay, when you move away from congruence modular varieties, they don't agree. Now I want to go back, and this is the confession slide. I misled you to think that higher commutators are useful for groups, and here's why. So we used all these properties of the higher commutator to solve Holt's question. However, if you think of the properties I used, I needed to know that this is an operation that's additive in each variable over the join operation, that the higher commutator is contained in the meet, and that it behaves well with respect to quotients. That's all we used about it. And there's a group theoretic word that does the same thing. This standard group theoretic word has all the same properties that I needed for that proof. So I didn't have to have the higher commutator. I could use the binary commutator in an iterative way, and this word has all the same properties. So I could have approached Holt's question that way by using this word. Now this word is not totally symmetric, while the higher commutator for congruence modular varieties is totally symmetric. So you might say, I prefer a totally symmetric one. Well, you can, if you're a group theorist, you can make it totally symmetric just by joining all permutations of the standard group theoretic word. Just take the standard K variable commutator word, permute the variables in all orders, take the join. then use that word in the proof to solve Holt's problem. It turns out that is the higher commutator in groups. That word is the K variable higher commutator in groups. Okay, so a group theorist never really had to learn about higher commutator theory. But if you move away from groups and you know your binary commutator, this will not be the same usually. It's just groups are nice. Groups are nice, and it happens that we can't teach group theorists new things, right? But we can teach other people new things, because this word constructed from a binary commutator will not be the same as a higher commutator. The higher commutator contains new information. And I want to say why. So in general, in the theorem that I mentioned, we had one commutator, one is zero. That's a stronger statement than this in general, but for groups they're the same. For groups they're the same, but for other structures, we're getting a stronger result by using the higher commutator than if we just iterated the binary commutator. Okay? Yeah, let me mention some results which tell us that the higher commutator really provides us with new information. So this is Bulatov's paper where he first published the Bulatov definition that Meredith introduced in his talk. He studied clones with Malsev operation on the set 0, 1, 2, 3. He proved there are aleph not many such clones up to polynomial equivalence, and he proved this fact. Any algebra on the set 0, 1, 2, 3, add some operations, including a Malsev operation, is completely determined by specifying its congruence lattice, its unary polynomials, and the higher commutator operations as operations on the congruence lattice. Now, on a 4-element set, there are only finitely many choices of a Malsev operation. There are only finitely many congruence lattices of algebras on a 4-element set. There are only finitely many ways of putting unary operations on a 4-element set. So how did we get aleph not many? It's because there are infinitely many different ways of putting higher commutator information on that lattice. Okay? Now, if I just looked at the binary commutator, there's only finitely many ways I can put a binary operation on a lattice of equivalence relations on a 4-element set. So if I didn't have higher commutators, but I only had binary commutators, this theorem wouldn't be true anymore. The higher commutators are giving you more information about the structure of the algebra than you can determine from the binary commutator, no matter how you compose it with itself. Okay? So this is a theorem that tells us the higher commutators really do provide new information. And I want to mention another theorem that also, it's more recent. It also tells us higher commutators give us more information. If I look at higher iterations of one commutator, one, they are decreasing. It's a descending sequence. So that one is the top congruence, one commutator one is a little bit smaller, one commutator one is a little bit smaller. It's true for any algebra. But what if it's a simple algebra? It only has two congruences, 0 and 1. If I look at this descending sequence, it starts at 1. It may eventually become 0, but then it has to stay at 0. It's just going to be 1, 1, 1, 1, 1 for a while, and then becomes 0, 0, 0, 0, 0. Those are the only possibilities, unless it stays 1 the whole time. Okay? And what Steve Weinell proved is you can have it be 1 as long as you want, and then it will drop down to 0 at any specified place. He has a construction for this. Okay? Now, if I look at the ways I can put a binary operation on the 2-element lattice 0, 1, that has this property that one commutator one commutator one is a descending sequence. If I had a binary operation, there aren't very many possibilities. I could say that one commutator one is 1, and that determines everything. Or I can say one commutator one is 0, and that determines everything. Okay, so there aren't very many choices of the ways you can put a binary operation on an algebra. But if you look at the entire sequence, there are infinitely many things that can happen. And that says you can't construct the higher commutator from the binary commutator. Okay, so we get new information. And we call it nilpotent or two-step nilpotent if after 2 stages of iterated binary I get to 0, and 2-step super nilpotent if the same number of ones, but I'm not iterating the binary commutator. I'm using the higher variable commutator. Okay, so I want to say a few words about nilpotence. It has a long history. I didn't know it before I started working on nilpotent algebras, but I'll just very briefly go through when did nilpotence begin to be studied, and when did supernilpotence become visible as a separate concept? So the word nilpotent comes, it means not having any power, and it was created by Benjamin Pierce in a book from 1870. He was interested in R algebras, and he was interested when a power of an element becomes zero. He called that nilpotent. So he introduced the word into mathematics. And he also introduced the word idempotent into mathematics, but it doesn't mean quite the same thing that we mean now. He meant that some power of A is equal to A. Nowadays, it's typically the second power of A equals A. We call it an idempotent. Okay, so nilpotents in groups, they were discovered before the commutator was discovered. Okay, and this comes from the work of Capelli. Right after Silo proved the Silo theorems, Capelli said, well, what can you say about finite groups where there's exactly one Silo subgroup for every prime? Okay, and he called those omega zero groups, and he studied their structure. Nowadays, that's exactly what a finite nilpotent group is. There's exactly one Silo for every prime. Okay, so they were studying finite nilpotent groups, and he wanted to well, okay, I won't go into the details here. Yeah, I won't go into the details. I'll just say that he wrote a paper and introduced the Frattini argument, and Frattini later wrote a paper saying, I'm going to use the same argument that Capelli used, and so he copied it into his paper, and now we call it the Frattini argument, but really Capelli originated the Frattini argument. Okay. Now, I mentioned in my first talk that we didn't learn that Dedekind had introduced the commutator word until 1896 in writings of Frobenius. So this work was done, finite nilpotent groups were studied before we had a commutator definition of what nilpotence might be. Now that historical fact was sort of copied over into loops. Loops are non-associative groups. So Bruck defined the center of a loop using words. He had an associator word and a commutator word, and he wanted to define the center as something that if you plug it into the associator or the commutator, it trivializes. Okay, so he defined what the center was, and then he defined centrally nilpotent loops as if you iteratively factor out the center until you're left with nothing, it's a centrally nilpotent loop. Okay, so these were not well behaved. That is, trying to copy the word definition, that is, using commutator words, trying to copy that over to loops didn't produce a good concept. But his students, George Glauberman and Charles Wright, did show that you have structure similar to groups if you deal with Mufang loops. That is, just as in the case of groups, if you look at centrally nilpotent loops, you get a decomposition as a direct product of prime power order loops. You get this prime power decomposition as we're familiar with groups. Okay. Now, Charles Wright worked a little more on this. Let's introduce this idea of multiplication group of a loop. That is, I want the maps given by the right multiplications, and I take all such maps, generates a set of permutations on the loop. So it's a group. And Charles Wright, who's a student of Bruck, proved that a nilpotent loop factors as a product of nilpotent loops of prime power order if and only if its multiplication group is nilpotent. So he starts with a loop. He says it's centrally nilpotent, not quite a good concept, but if the associated group, the right multiplication group, is also nilpotent, we get a nice prime power decomposition of the algebra. Okay, and I'm going to just skip over these comments. Michael von Lee in the 80s studied this for arbitrary algebras with a Malsev operation. So he has a Malsev operation, picks an element, calls it 0, and looks at multiplications given by the Malsev operation. In a nilpotent algebra, if you look at your Malsev operation and fix the middle variable as a constant, you get a loop operation. Okay, so this is a way of introducing a loop structure for nilpotent Malsev algebras. And he looked at the group of all right multiplications given by the Malsev operation and proved that a nilpotent Malsev algebra factors as a product of nilpotent algebras of prime power order if and only if the right translation group is nilpotent. Okay, that's similar to the group case, similar to the loop case. And some comments about this, which I'm going to just skip over. Okay, now moving from those particular definitions to a language independent definition, I'm going to call two polynomials twins. So I take a word in the language, I put parameters in for some of the variables, A. I think of this as an operation in the remaining variables. Now, if I change the A's to B's, I will call these two operations twins. Okay, this is not my language. Emil Kish introduced the term twins. It just means two polynomials built from the same term, but they differ in their set of parameters. Okay, those are called twins, and it's relevant in the binary commutator because you can rewrite the definition that an algebra is abelian by saying that twin polynomials have the same kernel. That's another way of writing what it means to be abelian. Twin polynomials have the same kernel. Okay. So I'm going to look at all operations on A that are twins of the identity function. And if this was an abelian algebra, say a module, we know what unary polynomials of a module look like. They're all Rx plus a constant from the module. Every polynomial of a module is a scalar from the ring times the variable plus a constant from the module. Now, if they're twins, and I look at a pair of twins, the scalar from the ring has to be the same. So twin polynomials are telling me I have two unary functions whose only differ in their constant term. Okay? What does it mean to be a twin of the identity function? It looks like the identity function except for the constant term. So it's a translation. So in the module case, you're in the twin monoid if you're a translation. So what is the twin monoid? It's the translation group. So in the module case, the twin monoid is the translation group. It's a way that doesn't refer to the signature. It doesn't tell you what are the basic operations. It's simply you have to know the polynomial clone and you can recover the underlying group as the twin monoid. That's true in modules. Okay, so it's a language independent way to recover the underlying additive group of a module. Okay, now I can start with, say, the symmetric group, which is a group, a loop, and a Malsev algebra, and perform all of these constructions. That is the right translation group of von Lee, RS3, the multiplication group of a quasi-group, M sub S3, or the twin monoid of S3, and they're related to each other. The von Lee translation group turns out to be isomorphic to S3. I'm just saying right multiplications of S3 acting on itself is isomorphic to S3. Okay, that's easy. The multiplication group of a loop, I allow left and right multiplications, and they commute with each other. If it's a group, the left multiplications will commute with the right multiplications. So I get S3 cross S3. Okay, and the twin monoid is not even a group. It's a larger monoid. It's not a group in the case of S3. But the point is that, first of all, twin monoid is language independent. The other constructions depend on the choice of language, but they all capture what exists beyond nilpotence to get us to super nilpotence. Okay, so here's the theorem. Theorem. What does it mean to be a super nilpotent Malsev algebra? These equivalent conditions are now, what does it mean to be a super nilpotent mouse of algebra? What is it beyond just pure nilpotence that makes us super nilpotent? So if you are in a congruence modular variety, and number one, if you have a finitely generated clone and you're a product of prime power order nilpotent algebras, you are super nilpotent. Okay, it's stronger than just being nilpotent. Two, that's equivalent to saying there's a bound on the rank of commutator terms. For groups, x inverse, y inverse, xy is a commutator term. And for rings, xy is a commutator term. And for algebras, in general, you can write down commutator terms that help you define the commutator. We bound the rank of those commutator terms. There's no doubly exponential function, which is a lower bound on the number of k-ary terms for each k. If you compute the number of inequivalent k-ary terms for each k, it doesn't grow fast enough to have a doubly exponential lower bound. There are very few essentially different k-ary terms. Okay. Last one, A is a finitely generated clone. It's nilpotent, and its twin monoid is a nilpotent group. All right, so this was proved before the word supernilpotent was coined. We didn't know how to talk about these algebras then. Bonley was in the early 80s, Fries-McKenzie was in 87, Bloch-Berman's papers in 89, and I worked on this a bit. I was visiting Joel Berman and I said we should finish this off, and he just said, you do it. Okay, so Berman didn't get on the paper, but we did talk about this a bit, and this was in 96, I think. And I contacted Michael Kenyon at the time, who wasn't at Denver yet, and I said, we're finding these two kinds of nilpotents, and one's nice and one's not, and we don't understand why. What can you tell me, since you know these quasi-groups and loops? And he wrote back and said, we know about it, but we don't know what to do with it. So he said, in loop theory, we know that there are these two kinds, but we just don't know what to say or do about it. And it wasn't until Bulatov's paper in 2001 that we had a connection with the commutator, and then later with the work of Eichinger and Ecker, where we had the name supernilpotent. Some examples. Okay, in groups, higher commutator is the same as the iterated binary commutator. You don't learn anything new from higher commutator theory if you want to do groups. Okay, a group is k-step nilpotent if and only if it's k-step supernilpotent. But move away from groups. Take any algebra where its term operations have a bound on the essential arity. As soon as the operations have more than n variables, they no longer depend on some of the variables. Then you will find that these cubes, you can define it in terms of cubes, the cubes start to trivialize when the dimension gets too big. And then the commutator just becomes trivial. It becomes zero. So that if you have these cubes and they're built from these starting special cubes that are constant on hyperfaces, let's say you have a bound of k on the arity of your terms. When you construct a subalgebra, as soon as you get past dimension k, then you're constant in some dimension. So if I take cubes and two cubes agree on all vertices but one, they have to agree on the last vertex because they're constant in some dimension. Okay, and this is totally unlike anything in a congruence modular variety, in a group or ring. These are totally strange structures if they have bounds on essential arity. Things like nilpotent semigroups. There's a huge number of different kinds of nilpotent semigroups. Here's a 6-element algebra. Start with an abelian group, add an operation. It maps the evens to 0 and the odds to 2. This is nilpotent but not super nilpotent, because if it were super nilpotent, it'd have to be a direct product of prime power order algebras. And this operation F was added. I started with Z6, which is a product of prime power order algebras. It's Z2 cross Z3. But then I added a function which destroyed one of the projection kernels. And that means it's no longer going to be a direct product. So it can no longer be super nilpotent, but it still remains nilpotent. This is the classic example. Everybody who wants to understand super nilpotent should study this example. Start with Z4, it does have prime power order. Add these, take the abelian group structure, it'll have a Mal'Sev operation. Add these multiplications. For every K, take the product of x1 to xk and multiply it by 2. That's a collapsing product, okay? If you only include finitely many of these extra multiplications, it will be super nilpotent. But when you include them all, it is no longer super nilpotent. Each new operation builds a higher dimensional cube, which is 0 on all vertices but 1. And on the last vertex, it's a 2. And you have those kind in every dimension. And I can take the constant 0 matrix and the one that's 0 everywhere except at one vertex, and they're just not going to agree on their last vertex. And if you have these operations of every arity, you'll have those of arbitrarily large dimension. And that stops it from being super nilpotent. Okay. This starts 3 last slides where I talk about theorems from the past 20 years where people have applied super nilpotence to various problems and found some results. But my time's up. So I'm just going to tell you, for those of you who want to look at slides, that there's a long list of theorems in the last 20 years where people have proved things about super nilpotence. I feel like there's a lot to do. There's a lot to do. This is an interesting new area. I especially like this last one that Peter Meyer told me about. It's not published yet. But if you start with any finite nilpotent algebra, the structure is a little bit more complicated than the super nilpotent case. But what they prove is that for a finite algebra, that if it's nilpotent, it will have a super nilpotent reduct. So somehow general nilpotent algebras are just slightly built over top of super nilpotent algebras. Okay, but anyway, I'm going to leave those. It goes up to, I think there are 11 different theorems, papers that have been written. In the last 20 years, I scanned what people have done on this, and about half of the papers that have been published further develop the theory, and half have new applications. And I just focused on the applications that I found from 11 different papers. But I'm going to stop now and not show them to you. If there's a way to access slides, you'll be able to see what those theorems are. Okay, let's stop there.
Okay, so I'll fill the space here. So earlier in the lecture, you emphasized how it's important to show that one commutator, 1.0 should have a strong property. Could you
strong consequence. Well, in the Mal'Sev case, it does have a strong property. That is that that these algebras are finite products of prime power order algebras, and the whole algebra must be equivalent to something in finite signature. Okay, so in a sense, they're very much like a nilpotent group at that point. Now, the von Lee result I mentioned, where he started studying this for Mal'Sev algebras, he proved a finite basis theorem, that if you have a finite Mal'Sev algebra of finite type, and it's a direct product of prime power order nilpotent algebras, it must be finitely based. Okay, we still don't know if that's true for ordinary nilpotent algebras. So we know it's true for super nilpotent algebras. We don't know if it's true for nilpotent algebras. Okay, so this sort of CELO decomposition of super nilpotent algebras is a strong consequence. If I stopped at just one commutator 1 equals 0, then from a very old result of Goom, it's polynomially equivalent to a module. If I do one commutator 1, just 3 of them, then there's a result of Madrinsky that it's almost exactly, it's just a slight expansion of a 2-step nilpotent group. But when you get to more factors, it's no longer related to groups at all. But it's still much closer than an arbitrary Mal'Sev nilpotent algebra. Okay, so I would just say that, I mean, nilpotence alone, I mean, nilpotence and prime power order decomposition, these are strong statements about the structure. Yeah. There is a nice paper of Idziak and Berman where they ask this question. Suppose I have a finite algebra, a finite type, and generate a variety, and I look at the number of k generated algebras as a function of k. Let k increase. and ask how many isomorphism types of K-generated algebras are there. And they say if it grows at a slow rate, then all the nilpotent algebras in that variety must be super nilpotent. Okay? And then they also have some structure about the non-nilpotent algebras, that they're very close to abelian in that. So I feel like we are learning that that super nilpotence is a strong statement about the structure of an algebra.
Thank you for the presentation. It was really very nice and interesting. I'm curious about among all these theorems and papers, is there any research about reciprocated lattices? This theory of super nilpotence. Is there anything interesting about that?
Well, I don't want to turn you off of higher commutator theory by telling you the truth. I mean, as soon as you have lattice operations, then the higher commutator will just be the meat. Okay, so an n-variable commutator will just be the meat of the incongruences. But residuated lattices have a multiplication, right? So you might be interested in monoids that are super nilpotent, for example. And no one knows, I mean, no one knows which monoids are super nilpotent. So I think if you just take the monoid part and ask, what are the super nilpotent monoids? We know the super nilpotent groups, okay? We know all nilpotent semigroups are super nilpotent. Maybe the classification is within reach, but I don't know the answer. Yeah, so if you're interested just in monoids.
Yeah. I mean, I said residual lattices, but I residuated homonoids.
Okay. Yeah.
Thank our speaker.